Hello everyone and welcome to the week 3 of InSight at Home. My name is Karen Lama. I'm a computational seismologist at the Los Alamos National Laboratory. My job is to use supercomputer to model how seismic waves travel inside the Earth and Mars. So on Monday you were shown a little video that come from this website, aris.edu, and I wanted to invite you to check out the material they have over there to learn a little more about seismic wave and earthquake. So here are some snapshots of that video you saw on Monday. And what I wanted to draw your attention to is the shape of the trajectory of the body wave. They are curved. This is telling us something about the Earth. It's telling us that as you go deeper inside the Earth, the material is more and more resistant. So the first effect of that is it's becoming more and more difficult for the seismic wave to go deeper and deeper, and so they have a tendency to bounce off the deeper part, and it's how you obtain that curvature of the trajectory. The other thing is that seismic wave travel faster in more competent materials, so body wave will travel faster if they reach deeper part of the Earth. So what I wanted you to know, guys, is that we seismologists, we use this type of information and other to make a map in 3D of the elastic property of the Earth beneath its surface, and from those maps you can actually say something about what is the structure of the Earth. Okay, so let's look at the answer to the question of the quiz. So body wave travel faster than surface wave. P wave are compressional waves, so they are not shear wave. S wave always arrive after P wave. And on this little video you could also see that no S waves were reaching the station D. So you need two things to have a wave. You need to have an excitation force and a counter force. In the case of the seismic wave, the excitation force is the earthquake, and the counter force are the elastic wave, or if you want, the resistance of the material to the motion. So you can do this experiment with a bucket of water and do some compressional movement with your hands and shear movement. And you will see that in the shear movement, you cannot feel any resistance of the liquid. Because there is no resistance of liquid to shear motion, you cannot have S wave in liquid. And so that's the reason why we didn't have any S wave at the station D. And by the way, the absence of S wave is how the liquid outer core of the Earth was discovered in the beginning of the 20th century. Okay, so on Tuesday we learned that during the Apollo mission, the astronaut put several seismic stations on the moon. So you were given those records of the impact of Saturn 16 on 3 stations with their arrival time of the P wave. And what you have to notice is that the arrival time are very similar between the 3 stations. There is a variation of about 14%. So from the 4 locations proposed, the most probable is the location B, because that's the only one that is somewhat in the middle of the station network. So you were given this map, which has this ruler, and you can use that to compute what is the distance of each station from the impact. You can also take the arrival time of the P wave and compute like that an average P wave for each station. So here I order the station from the closest to the furthest, and what we noticed during this little experiment is that the P wave is noticeably increasing from between those 3 stations. So this is telling us that the moon is like the Earth. As you go deeper, the material is more competent. So this is telling us that the moon is a differentiate planetary body like the Earth. this little experiment of ours too is your first step inside the moon. So congratulations. Okay, so the only statement that was wrong here is that P wave don't propagate in all directions. And the reason why there is no seismometer from Apollo 13 is because that mission never landed on the moon. Okay, so on Wednesday, we went back on Mars, and you were asked to use that little website, which is pretty neat. You can both have numerical modeling of the seismic wave for different model of Mars, but you can also look at actual record by the lander, and you were asked to look at the record for Sol 235 and look at the arrival time and the odochron. The odochron is the arrival of the P and the S wave versus the distance of the source from the recording station. Okay, so using the tool, you could determine the arrival time of P and S wave and determine that the difference of arrival time is about 157 seconds. Okay, next was to use the odochron and to determine what distance from the source is needed to explain such a different time between the P and the S wave. And so we know that the marsquakes was located about 1,500 kilometers from the lander. Okay, next you were asked to look at waveform recording by InSight. So what you need to remember is that you have three directions corresponding to the three directions of space, and what was noticeable for that event is that the most important horizontal movement is in the east-west direction. So that suggests that that event was located either to the east or to the west of the event. So if you put those two pieces of information together, the distance and the direction, you can determine that that marsquake was coming from the area of Cerberus Forcea. What is interesting to know is that InSight first recorded several events that seems to come from this area, and second, satellite image of the area show evidence of volcanic activity in that area that are relatively recent for Mars. We are talking about the last million years. So the scientists are very excited by that discovery because it may mean that there is still some magma moving in that area on Mars. Okay, so with the previous activity, you learn how it's critical to know in which direction the seismometer is located. But on Mars, there is no longer a strong magnetic field, and we haven't set up a GPS network over there yet. So we don't have the same. So we don't have these two things to locate the north. So the engineer of InSight used the technique of the sun dial. That was a technique used by our ancestors before the introduction of the compass. That technique consists at monitoring the shadow created by the sun from a small stem, and from that determine where is the north. So the only statement that was wrong here is that that stem is not bending as the sun passed by the lander. Okay, and so the reason why we use that method is because there is no longer a magnetic field on Mars. Well, thank you for taking that trip to Mars with me.